One of the more visible signs of the technological revolution sweeping the Russian armed forces is the proliferation of battlefield robots being tested for use with the ground forces. The range of programs suggests this is a high priority for the Russian Ministry of Defense, and the existence of such weapon systems is indicative of the importance being placed on implementing the digital revolution in the armed forces to make them capable of waging net-centric warfare relying on small units operating independently without a well-defined front line. The most important robotic system under development for the ground forces is the 6-ton class Uran family of tracked vehicles, which include the Uran-6 minesweeping vehicle and the Uran-9 combat vehicle, whose armament includes a 30mm Tu-A72 automatic cannon, Ataka laser-guided anti-tank missiles, and Igla or Verba short-range anti-aircraft missiles, which collectively allow it to engage all battlefield targets. Russian industry also has smaller vehicles under development, such as the Nerechta and Platformer M systems, whose modular design allows them to be armed with machine guns, automatic grenade launchers, anti-tank guided missiles, and RPGs. There is even a miniature, backpack-portable, assault rifle-armed battle robot named Strelok that is capable of climbing stairs, and miniature quadricopter drones armed with grenade and flame launchers. The most ambitious initiatives include a robotic version of the BMP-3 infantry fighting vehicle named Udar and the remote control feature built into the Armata family T-14 tanks, which enables individual T-14s to be controlled by other T-14s through the provision of high-volume data links which give complete access to the sensors, weapons and controls of the vehicle being controlled. Instead of relying on satellite communications, which combines long range with vulnerability to jamming and hacking, Russian battlefield robots are controlled using short-range communications of no more than a few kilometers in range. The above-named and other systems are in advanced stages of development and troop testing. There are reports that some of the robotic weapons platforms were deployed for battlefield testing in Syria. While the reports of them spearheading assaults on jihadi positions in Syria while under control by Moscow-based operators are likely exaggerated, battlefield robots are being developed to perform two kinds of missions. The comparatively small size of modern armies means that stable front lines will be rare in future warfare. Even the small in size Donbass theatre of operations has a front line consisting of checkpoints, fortified positions and garrisoned towns, rather than continuous trench lines, which presents both sides with opportunities for infiltration. It means that every unit has to worry about providing its own security and protection, both when occupying permanent positions and on the march. And the robots can provide that capability by performing surveillance and patrolling roads to discover ambushes and roadside mines. The other mission is overcoming prepared defences, including in urban terrain. The lethality of modern weapons means that offensive operations against opposing units in strongpoints or urban terrain are likely to suffer many casualties. While such resistance can be reduced through massed artillery or aerial bombardments, such tactics also cause unacceptable losses to civilian population and damage to infrastructure. Armed battlefield robots can perform armed reconnaissance by compelling defending units to reveal their positions by prematurely opening fire, clearing minefields and obstacles, and destroying individual strongpoints. The development of a modern armour force, deployment of the Ratnik individual soldier suite, and the work on battlefield robots is aimed at ensuring the Russian ground forces can prevail not only in mobile armed warfare, but also in the positional slugfests that have characterized the recent armed conflicts around the world.
Hey, this is Norm from Tested.com. I'm here at the DARPA Robotics Challenge, where teams from across the world have brought their robots and their software to compete, trying to build a robot that's good for not killing people, rescuing people. Now I'm here with Katie Bills. Katie, you're a robotics professor at UC Santa Barbara, working with JPL on a robot that doesn't look like a humanoid robot. Tell me about RoboSimian.
Well, a lot of teams have taken a humanoid form because we think we would be good at these tasks. But if you think about it from the perspective of what you'd want in a rescue scenario, it's things like stability. So RoboSimian's designed with 4 limbs, and strength. So this is a robot that's really designed to be able to do pull-ups, for example, to be able to clamber around on a jungle gym, as opposed to being a little bit more delicate and human-like in form.
Let's talk about the stability angle first. Now, with a bipedal robot, we take walking for granted, standing for granted, but when you're on 4 legs, what can you do when you have legs of equal dexterity and strength?
With legs like RoboSimian's, you can really reach far, and you can really take advantage of a lot of complex geometries. So for the bipeds in there, you notice even though the terrain has some slopes to it, those cinder blocks still give you a nice flat surface. With a robot like RoboSimian, we could really just deal with gravel, even sharp pointy rocks, because you basically have a table. You've always got 3 legs of support. If something slips underneath you and the robot falls by a few degrees, it's not really falling, it's just readjusting itself.
And so in designing the software and the algorithms to walk in a 4-limb gait and even be able to stand up on 2 legs, what type of situational awareness does a robot need to have of the environment and of its own body?
Well, the robot needs some sort of map of the environment and some sort of way to decide what is a reasonable foothold or not to use. A lot of quadrupeds, they only really care about like the end effector of its foot, like where the last point is going, like the XYZ position. But this robot, since those legs also have to be used to hold tools, it cares about 6 degrees of freedom. So XYZ and the roll, pitch, and yaw, that's great for manipulation, but for locomotion, it means those degrees of freedom can potentially get itself tangled. So if you think about playing Twister and you don't plan about it well in advance, that's the program that can happen with mobility for RoboSimian if you're not thinking carefully about where to put all those degrees of freedom, all those actuators.
There's a lot of elbows going on over there.
A lot of elbows. Basically, it's a robot that has 3 sets of elbows. So if you think about 2 ways to put each elbow, there's often 8 different solutions on how I'm gonna twist my joints around. And the robot's essentially unfurling its limbs when it wants to take a really long step.
So what are the advantages of having that type of design where you have so many joints, so many points of rotation, actuation? Is that for that dexterity, for actually using the legs as an arm,
Exactly. You could imagine designing a centaur that has 4 legs for mobility and another 2 limbs to do manipulation. But that means you have to use more batteries to carry that much more weight. Why not just use the same limbs to do both? So that's exactly what we're doing.
And I know JPL also, for this challenge for DRC, developed a robot called Surrogate, which uses similar arm structure. It looks like these arms are very versatile. They can be more than just arms.
Absolutely. The arms use the same geometry for each of those 3 links, basically those elbow joints we're talking about, the same actuator and each one of the degrees of freedom. And Surrogate basically uses the same identical limbs. It's a little bit not obvious when you look at it. 2 of them as arms and a 3rd one as a torso. So it can basically use an arm as its body to orient around where its head is pointing, and then use the 2 real arms to actually manipulate things and lift things with 2-limbed dexterity.
Now with that type of spider-like movement, even we're seeing in the video, for example, the robot's not moving that fast. Can you walk us through just a step-by-step?
I should be honest, this is actually sped up 7 times to look reasonable there. So this is a robot, like I mentioned, that's designed to do pull-ups. There's a trade-off between speed and torque, right? So if you're riding your bicycle and you want to go up the hill, you switch to a gear where you have to pedal like mad and you're going slowly. So the robot moves at about 1 radian per second, like 60 degrees per second. It's like 1/1000, 2/1000, 3/1000. But it's very powerful, strong enough to do pull-ups. So because of that, you're going to see the robot moving slowly and deliberately. But unlike some of the other robots, if something's in the way, a rock, it can probably just push that right out of the way because it has that strength.
One of the parameters of this challenge is the robot has to get out of a vehicle and get to the location. That might be more suitable for a robot that's humanoid, but RoboSimian also, surprisingly, can sit in that vehicle. Is that one of the bigger challenges for it to get out?
On the one side, we thought that the driving would be the most challenging thing because trying to get the robot into the car is so crazy. once we actually started working on it, we realized in some ways we are at a real advantage in the car. You can see how complicated it is to try to twist its leg out right there, because the chassis of the car is sort of like a jungle gym. So we have stairs in the contest, but they're actually pretty easy for a humanoid to do. They don't even have to hold on to the rails. We would really excel if we had something more like a jungle gym or a ladder that required, like, imagine all four of the limbs had to grab onto a ladder. That's actually more similar to the car egress, where RoboSimian really performs highly reliably.
And think about robotics in general. A lot of the parameters of this challenge, specifically and other designing robots, is to make robots that accommodate the world that humans live in, the stairs and the cars that we have to use. When you're, as a roboticist, do you think it's better to design robots that are more versatile, for other types of environments that humans have no place in?
There's definitely a place for both. So most of the robots that we're going to be interested in, robots in the home, they're going to have to deal with, the important word is variability. So they have to deal with human-like environments, but maybe your dog is sitting on the floor and you don't want to step on the dog. Maybe you've got a split level, floor. Maybe all the kids' toys are sitting out there. You have to be able to deal with that. There's also a place for robots that can go places where it's not safe for humans. That's definitely more the direction that this is aimed at, for both Terran environments and potentially in outer space, and potentially, speaking of Terran environments, I don't mean necessarily the ground, in the water. There's an Aquasimian that's in the design phases right now that would be able to work like the Deepwater Horizon, that kind of scenario where you could climb around to repair things.
So Simian as a platform, what JPL is doing is not only for for Earth, but space, but also just different environments going forward as well.
Exactly. Any environment that's got complex geometries, that needs some unique mobility to be able to have surfaces to grab onto, and where you need high degrees of freedom to kind of open up your options, to give you a larger menu of things you can do. And as I keep mentioning, to have that strength so you can really operate the world around you. So I think we designed this robot thinking about what's really useful in a rescue scenario. 18 months ago when we saw the DARPA trials, I think it was like light bulb for a lot of teams, like we could just design a robot that can just do the DRC. So a lot of the robots have a morphology which is fantastic for the DRC. I think if I were picking a robot for a real rescue scenario, a robot like RoboSimian or Chimp would probably be my top picks.
So these robots are paired with human controllers. They're not fully autonomous. What's the difference between a robot that you have human control and some degree of autonomy, and a robot that you see like building a car that's used for just fabrication?
Right, exactly. I mean, robotics has been around for a long time, and there was flourishing in the 80s. Those robots are really designed for a planned, we think about the term robotic, repeating kind of set of tasks. So if I have a robot where I can bolt it into the ground, and I'm moving the joints around, and I know exactly where a car is and exactly where I'm going to do the welding joints, the term robotic we think of as meaning doing the same thing again and again. Now, these days, we think of robotics having a lot more flexibility. The key word I would say is variability. These days, we really want robots that can deal with a whole variety of tasks. So one thing that's important is that the robot is no longer mounted to the ground. It has to be able to travel around and be able to manipulate objects in its world. So you'd like to have a set of behaviors that you can do, but not scripted behaviors, not where you do exactly the same thing. It's a set of behaviors that have to be robust. And robustness really means being able to be reliable when you're subjected to variability that you can't always predict.
So Katie, another thing that humans, we take for granted in addition to standing, something simple like opening a door. What goes through the robot's software and programming to get it to open a door? What is the challenge there?
Right, yeah, we take it for granted when we're opening a door. You may have walked into a fancy building where you pull on the door and you're expecting it to rotate about a hinge. It does something a little bit unexpected. A human will just go with the flow. You feel those forces and you react. The robot is going to do exactly what you tell it to do. So if you tell it to open a drawer and it's pulling it outward, it assumes that there are certain degrees of freedom. There's certain affordance. It's going to slide on rollers. If you're opening a door with a handle, it normally rotates about a hinge. So if you tell the robot, just something like pull on the handle, and it pulls outward like this, you could just rip the handle off if you're strong enough. In fact, in the trials 18 months ago, we had practiced with a turning door handle that was used to turning 90 degrees. And in the trials, the door handle was only going to let you turn 70 degrees, and we broke the fingers on the robot because of that.
So it's about a measure of feedback. Again, it's that situational awareness, not just what's around the robot, but what's in contact with its own limbs, its own strength. That's something that the robot needs information on.
Exactly. There's two approaches to deal with that. One is that you have a menu of varieties. An operator can say, okay, I need to understand that it's rotating about this degree of freedom and not sliding. The second is what you said. You're going to need to use feedback. And that's really the preferred method. You'd like to do both. You'd like the robot to have the best information it can when it does a plan, but it needs sensors to say, wait, those aren't the torques I expected to feel. Like, I need to stop and reevaluate and understand that things are moving in a different way and plan. That is a really tough challenge and one that we're still trying to address in the field.
Thank you so much, Katie, and good luck to your team.